Welcome to our October AusIMM Perth branch technical meeting. My name's Ivor Roberts. I'm on the Perth committee and my role is to assist in the organisation of these technical talks. Tonight we've actually got two speakers and both of them are from Murdoch University and they're doing their PhDs. The first talk is Anna, the lawyer. And she'll be talking about her studies, PhD studies on nickel laterite. Anna moved from Italy to the United Kingdom for undergraduate studies in chemistry, obtaining a Bachelor of Science degree from King's College, University London in 2010. After moving to Australia in 2000, Anna began studying towards a PhD in extractive metallurgy at Murdoch University. What we'll do, her presentation is around about 20 minutes. We'll then have questions and then we'll have the next presentation after that. So would you please put your hands together to welcome Anna to the podium.
Hello everyone. So as already introduced, I'll be giving you an insight into my PhD project which I've been working on for the last few years. The outline is that I'll be giving you an introduction to the Caron process, or why it's still relevant to speak about the issues with it, a bit of background in the chemistry of the leaching stage of the Caron process, and then the focus of my project. And after giving you details of the experimental setup which I've used for the investigations, I've summarised the main findings resulting from my research. So, to introduce the Caron process, it's a combined pyro and hydrometallurgical process to extract nickel and cobalt from laterites. As most may know, that most of the land-based nickel source is laterite, with the lower amount coming from sulfides. However, most of the nickel is extracted from sulfides rather than laterites because of the ease of because it can be easily beneficiated and concentrated. However, the growing demand in nickel is being predicted to be met by laterites rather than sulfides because of there being a higher abundance and more ease of access. Therefore, generally, laterite ores are more usually they are extracted using acid leaching techniques. However, the drawbacks of the more common acid leaches are the high reagent consumption due to the presence of acid-consuming species and the dissolution of high amounts of impurities which make it more difficult to separate and purify the final product. The Caron process overcomes these two main drawbacks of the acid leaching techniques by using a lixiviant that can be regenerated and recycled into the leach, therefore reducing the expenditure due to reagent consumption. And also by employing more selective lixiviant, so it targets more specifically the metal values with less dissolution of impurities. Currently, there are not many Caron plants active, so there's a few two in Cuba, and in Brazil there is one, and then in Australia there's the Yabulu Queensland Nickel Refinery. The reason why there are so few is possibly related to the low extraction efficiency of the process compared to other techniques, with only 80 to 82% being achieved in nickel being achieved at the Yabulu plant, and cobalt even lower extraction efficiency of 50 to 60%. So there's a significant problem which is causing this low popularity of this process. So here's a flow sheet of the refinery in Yabulu. The two main parts of the process are the roasting of the ground ore, in which the laterites are basically roasted under reducing conditions. And this is followed by ammoniacal leach, initially under oxygen-free conditions in the first of the larger of the tanks, followed by leaching, which is carried out in aerated conditions in the following 4 tanks. So this is the part of the process that I'm interested in, looking at what problems may be limiting the efficiency of the process. And so to look at the material that I'm studying, the solid material, I have to go back one step and look at the reductive rows. So there's the laterites, in which the nickel and cobalt are present mainly as oxides and silicates, is roasted under reducing conditions. And in this step, the 80% of the nickel and cobalt are reduced to the metallic state. And because of the presence of significant amounts of iron, there's quite a significant amount of metallic iron also reduced, since 20% of it approximately is reduced as well. So the nickel and cobalt are mainly present as alloys with the iron. Also, because of the presence of sulfur in the fuel oil used in the reduction, there are also some sulfides being formed during this step. So when this reduced material is fed to the leaching tank, it comes into contact with the solution which already contains dissolved nickel, cobalt and thiosulfate ions. The thiosulfate derives from the leaching of the sulfides, and this is because the solution is recycled from the countercurrent washing circuit into the first of the tanks. So what's important is the contact of these metals with the solutions that already contain these dissolved metals and thiosulfate species, and any interactions that might take place between the solid and the solution. So it is quite a complex, the chemistry of the leaching is quite complex, but the main reactions taking place are the dissolution of nickel, metallic nickel, which is taken into solution by forming nickel amines. Again, cobalt as well. It goes into solution and is oxidized to cobalt amines, which is then further oxidized to cobalt-3 amines, which also act as an oxidant, so further oxidize more metallic nickel and cobalt. Iron is also brought into solution during any metallic ion present, by forming amines, but then further down, when the tanks are aerated, it is oxidized to iron 3 hydroxide and precipitates out, hence the selectivity also of the process. It rejects the iron by precipitation. Thiosulfate is also present and acts as an oxidant, and aside it has also reduced the sulfide, which in the presence of metal ions already in the leach solution may precipitate sulfides also. And this is also another important aspect which needs to be taken into account, because if the metals are cobalt and nickel, well, then there's loss from solution of these metals, and we need to study how fast these actually redissolve once they're no longer in contact with the metallic species which are reducing the thiosulfate. So because there's a lot of metallic iron in the reduced ore for the reasons already described, the nickel and the cobalt is present as alloys with the iron, and what previous studies have shown is that the behavior of these alloys is significantly dominated by the behavior of iron. So many of the iron, nickel and iron cobalt alloys are basically behave very similarly to just iron. So it makes sense to simplify the problem and study the behavior of iron, because it's whether it's on its own or together with nickel and cobalt, it is likely to have a strong influence on the dissolution, because also you need to dissolve the iron to be able to get to the nickel and cobalt in most cases. So to investigate this, I've used electrochemical techniques with the use of a potentiostat connected to a 3-electrode cell, in which the working electrode for most of these studies was iron, made of pure iron. Reference electrode to enable me to measure the potential of this iron electrode. And for those experiments in which I vary the applied potential, I used a platinum counter electrode as well. The solutions used for the experiment were chosen to replicate the solutions used in the Caron process, with being mainly all of them being ammonia and ammonium carbonate. So I here referred to total ammonia being ammonia and ammonium ions, and carbon dioxide referring to carbonate and bicarbonate species. Also, I studied the effect of having different combinations of other ions, metal ions which are usually present in the current leach solution, nickel, cobalt, thiosulfate, and copper, which is present in some plants at higher concentrations. In the Yabulu plant, there's not much of it, but in other plants there may be higher amounts. So the main measurements I conducted with this setup are open circuit potential measurements, which are just looking at the real situation. I'm not applying any current. I'm not doing anything particular to the iron. I'm just looking at its potential and monitoring it and seeing whether it's still actively dissolving. And because the potential can tell me a lot of things of whether it is active or passive or what is happening. But also I need to combine it with some voltammetric measurements in which I apply a potential and look at the current response, which can give me an insight to what reactions are taking place and whether the iron, again, it tells whether it really is active or passive and what other species might be present at the interface. So overall, the main findings are that iron in most of the solutions of combinations of the ions present generally would remain active, and this is necessary, as I said before, to liberate the nickel and cobalt. However, there are specific solutions, specific conditions in which the iron, and similarly iron nickel and iron cobalt alloys, are passivate, which means they stop dissolving, and therefore, if it is an alloy, it can lock in the nickel and the cobalt. The specific conditions in which this has been found to take place is in the presence of copper, even at very low 0.1 gram per litre amounts, or in the presence of both cobalt and thiosulfate ions, though this does take place at a slightly lower total ammonia concentration to those employed at current plants generally. And there's another aspect which may be affecting the efficiency of the process, and that's that during the dissolution of iron, there's this formation of the sulfides, since the thiosulfate acts as an oxidant and is reduced by the iron and can form nickel and cobalt sulfides, which in itself cause further losses as they don't remain in solution. So in the presence of copper, in the first case of passivation that has been observed, you can see that at the concentrations of copper, quite low concentrations, which are found at the Yabulu plant, which is the lower curve, the potential of iron versus time doesn't really change much. So it remains in what is known to be the active dissolution region, and at the end of this observation of the iron surface shows that there's been deposition of copper, of metallic copper, onto the iron. These dendrites have been formed whilst the iron is dissolving, so it's been a metal displacement reaction by which the copper is displacing iron and is depositing onto the iron surface whilst the iron is dissolving. In the case of a higher copper concentration, you see there's a change in the open circuit potential. So initially, again, there is a potential which remains in the active region, and there's a deposition of copper on the iron surface. But then there's a steep transition in the open circuit potential to an intermediate potential. And observation of the surface shows that there's still some copper on there, but it appears to be thinning. And this potential at which the electrode pauses for a moment is actually the potential of copper dissolution. So the iron dissolution has ceased, and now the copper starts redissolving. So it's no longer acting as a cathode, it's anodically dissolving. Once all the copper is dissolved, what's left behind is just an iron surface, but it's actually passive, so it's covered by a thin oxide layer which prevents further reaction. And this, in this case, it happens within 10 minutes at 0.8 grams per litre of copper, but it can take place at 0.1 grams per litre at just longer times. Similarly, you see the same behaviour with iron nickel and iron copper alloys, iron cobalt alloys, which represent what we may find in the reduced ore. And you have this initial active dissolution followed by no longer dissolution of iron, and then the dissolution of copper, which is intermediate. Once the copper is all dissolved, the iron is passive, and any nickel and cobalt present in the alloy is not going to be recovered. The fact that iron is passivates in this transition is confirmed by voltammetric measurements. We don't need to go into too much detail here, but if by varying the potential in a scan prior to the open circuit potential transition, you see that there is oxidation of iron, meaning that iron is still active at this stage, and then it's followed by oxidation of the copper as you increase the potential. And once all the copper's dissolved off the iron, as you increase the potential further, there's no longer any current. And then it's scanned back in the reverse direction and you don't get any current. Then you start to get a reductive current and again, dissolution of iron. When after passivation, you don't get this behavior because the iron is passive. So we're starting from a potential of about 0.1, where I've marked OCP, and we'll get no current because the iron is actually, in fact, passive. This confirms that it's passive. You only get reactivation when you scan it in the negative direction and make it more cathodic. Then you get reactivation of the iron. This passivation has been found to be to take place faster for increasing copper concentrations and for lower ammonia and carbonate concentrations. So both the ammonia and the carbonate delay passivation. The other case in which passivation was observed was when both cobalt and thiosulfate were present in the solution. You can see here in the lowest line, when there were 2 grams per litre of cobalt, the iron remained active, and that's quite a high concentration of cobalt, and still it didn't have a similar effect to the copper. Whereas when both cobalt and thiosulfate were present, even at much lower amounts and even at the typical concentrations found in the Caron process, you get a transition to the passive region. And observation of the surface following immersion in both cobalt and thiosulfate solution, you get this surface layer, which is thought to be a cobalt sulfide layer. It's confirmed to be, but couldn't get a specific stoichiometry or a specific phase because it appears to be amorphous. The cyclic disk voltammetry shows that prior to the OCP transition, you get an iron oxidation peak, which is somewhat suppressed. So this layer appears to be reducing the maximum current reached with by the iron oxidation. So it suppresses the oxidation, the dissolution of iron, and then once the transition has taken place, there is no longer iron oxidation as expected, and the OCP starts at a higher potential, and there is still something on the iron surface, which is the cobalt sulfide, and it's being oxidized. So it's a different case to the case of copper, where iron passivates and the copper is then redissolved. No, in this case, the cobalt sulfide remains on the surface. Before passivation, it seems to suppress the dissolution of iron, and after passivation, it is still on the surface. So it's interesting to know how long it takes to redissolve, because if it doesn't redissolve fast enough, that will account for some losses of cobalt. And again, the timing of passivation it takes place faster for higher cobalt and thiosulfate concentrations, for lower ammonia concentrations, but in this case, increasing the carbonate concentration appears to make passivation take place faster, which is the opposite to what had been observed in the case of copper. The other issue that I mentioned is the formation of sulfides. Unfortunately, I couldn't get an XRD pattern of the cobalt sulfide, it being amorphous, and it's actually the most important sulfide which does form and requires further investigation with regards to how fast it redissolves. But in solutions containing nickel and thiosulfate, I was able to determine that on the iron surface there was a nickel 3s2 phase, possibly other ones which are not crystalline and weren't shown in the XRD. And also in the system containing copper and thiosulfate, there was the formation of a cuprous sulfide. And also, in this case, significant amounts are formed and they fall into solution as well and remain undissolved for an indeterminate time for the moment. And these filtration of the solid shows that it does contain cuprous sulfide as well as a mixed copper iron sulfide. But as I said, the most important sulfide, which seems to have a stronger effect on the dissolution of iron, is the cobalt sulfide rather than these ones. So in conclusion, to summarise my results, the main findings have been that there are certain conditions which can promote the passivation of iron, one being the presence of even very low amounts of dissolved copper, and the presence of both cobalt and thiosulfate, although this takes place at a somewhat lower concentration of ammonia. And more importantly, the formation of metal sulfides, of which the cobalt sulfide appears to suppress the iron dissolution, as well as promoting passivation, as already mentioned, and may in itself, regardless of whether passivation takes place, it may account for further losses of cobalt simply into this layer. For more details, there are 2 papers that cover some of the work shown here. And I'd like to thank you all and to thank my supervisors. And if there's any questions.
It might be a simple question for you, so sorry, but I noticed that you're looking at the iron and looking at cobalt and thiosulfate. Did you look at thiosulfate by itself without the cobalt?
Yeah.
And
it doesn't cause passivation. It doesn't seem to have any. Well, it increases the dissolution of iron on its own. The thiosulfate acting as an oxidant without any other metal ions present, it has a beneficial effect on the dissolution of iron. Yeah. Okay.
Our next speaker is Rorie Gilligan. Rorie will be talking about refractory uranium ores, and in particular brannerite. Like other refractory uranium minerals, brannerite requires extreme conditions for leaching to be effective. Rorie will present his research on brannerite, specifically the effects of temperature and acidity on the rate of uranium and titanium release, as brannerite is a uranium-titanium mineral. Rorie completed bachelor degrees at Murdoch University in 2011, majoring in chemistry and extractive metallurgy. In 2012, he commenced his PhD research in metallurgical engineering. So please put your hands together to welcome Rorie to the podium.
All right. Hello. So for a bit over a year now, I've been studying the leaching of refractory uranium ores, specifically those containing the mineral brannerite. It's fairly difficult to process compared with other uranium minerals, of which there are many. I'll start with a bit of background about uranium leaching and the mineralogy of brannerite before getting into some of my experimental results. So it's a mixed oxide of uranium and titanium found in a few uranium and rare earth deposits. Ideally, it's uranium-titanium oxide, but minerals are seldom of their sort of ideal composition. Thorium and some of the light rare earths can replace uranium within the lattice, and there's often a bit of lead in there as well, formed as a decay product of uranium and thorium. In the ground, within these sort of uranium ores, it's often associated with other titanium mineral phases, such as ilmenite and rutile. Compared with other uranium minerals, like other multiple oxides of uranium, it requires relatively intense conditions, which I'll be getting into shortly. There are worse uranium minerals out there, like davidite and petrifite, other mixed sort of multiple oxides, but they're not quite as common. Of the uranium minerals considered refractory, brannerite is one of the most abundant. A lot of the uranium lost to mill tailings is bound up in these kind of refractory mineral phases. It's been identified in a few deposits around the country. There's thorium substituted brannerite's been identified in the Crocodile deposit in South Australia. It's been identified in some of the uranium deposits near Mount Isa in Queensland, and it's also a minor uraniferous mineral over Roxby Downs. Elsewhere in the world, it's been mined in Ontario and Canada. Yellowcake is produced from high brannerite ores in Ontario. I think those mines are still in operation. Let's see. Yeah, relatively intense conditions were used with residence times of about a couple of days. That's what they needed to get some sort of. That was what was required for adequate recoveries. And it's a fairly large deposit in Siberia that's been known for about 40 years, which is the main uranium mineral. So, before I get into the specifics of the leach process for brannerite and my own experimental results, I'll just run through the basics of uranium chemistry. So it exists in a number of different oxidation states, but there's only about 2 of them that are really important for our purposes: uranium-4 and uranium-6. Uranium-6 is amphoteric, reacts with both acids and bases. It's a lot more soluble in water compared with uranium-4. Now, most uranium-bearing minerals contain uranium-4, so it's necessary to oxidize it over the course of leaching. It's necessary to oxidize it first again to get it into solution, which is why most uranium leaching processes take place under oxidizing conditions. There are a few minerals out there that contain uranium as uranium-6. These are mostly ones that form sort of weathered deposits, so it's been naturally oxidized already. It can be leached under acidic conditions or alkaline conditions. The choice between the two depends largely on the mineralogy of the gangue. If there's too much acid-consuming gangue, then acid leaching will become uneconomical. While the process of acid leaching is described as acid leaching, it's more like acid-facilitated oxidative leaching. The acid works to keep the uranium and iron in solution. Iron, which is being used as sort of oxidative medium. Iron sulfate and sulfuric acid are the standard sort of reagents for acid leaching. The iron will dissolve from the ore itself, but it can also be added to sort of increase the oxidizing strength of the solution. Iron 3 oxidizes the uranium-4 within the mineral to water-soluble uranium-6. And this the resulting iron 2 is converted back to iron 3 through the addition of oxidants. Pyrolusite, manganese dioxide is a fairly common one, but hydrogen peroxide, sodium chlorate, oxygen gas, bubbled into solution have also been used elsewhere. The example reaction I've shown down the bottom just shows the leaching of uraninite with manganese dioxide as an oxidant. Relatively mild conditions can be used most of the time. Atmospheric leaching is generally effective, with a bit of acid needed to keep the iron in solution. Lowering the pH will speed up the uranium dissolution, but it will also increase the rate of gangue dissolution, which in turn increases reagent consumption, so it's not always worth it. Heating may be necessary and, again, will increase the rate of uranium dissolution, but may also speed up the gangue dissolution more than it speeds up the uranium dissolution, and therefore might not be worth it. Oxidants will need to be added just to keep it under fairly relatively oxidizing conditions, just to get the uranium in solution, keep it soluble. The higher the oxidizing potential, the more iron will be present in the usable ferric state. So, now, specific to brannerite, alkaline leaching is not known to be particularly effective for it, so we're restricted to working under acidic conditions. Same sort of reagents are used, just more of them, higher reagent concentrations, and usually working at elevated temperature as well. The reaction between brannerite and ferric ions is similar to the example reaction I showed earlier, with uranium being oxidized, entering solution as uranyl sulfate complexes, with the titanium dioxide product being left behind. The titanium will dissolve as well, partially. The process is actually a bit more complicated than this, but I'll get into that when discussing the details of my results. So I was not able to find too many industrial examples, but under typical leaching conditions, brannerite will dissolve quite slowly, if it does at all. So for this reason, relatively intense conditions are needed. I say relatively intense rather than intense because these sort of conditions may be normal or even mild compared with the leaching of some other commodities. So higher concentrations of acid are used, typically around upwards of 50 grams per litre sulfuric acid, which corresponds roughly to a pH of 0.3 and below. Higher temperatures, even pressure leaching has been suggested. But even under these, more strongly oxidizing conditions as well. Even under these conditions, though, dissolution will still be slow. The Canadian mines I referenced earlier leach brannerite in 60 to 75 grams per litre sulfuric acid, about 75 degrees, the residence times of a couple of days needed for adequate recoveries. In the first series of experiments, the ones I'm presenting on today, I studied the effect of sulfuric acid concentration and temperature. There have been a few papers on the rate at which uranium is released from brannerite and brannerite-containing ore, but not that much on the behaviour of titanium, which I suspect may also be of importance. It's also necessary to study brannerite dissolution in isolation from gangue as well. There's many ways in which the gangue mineralogy can influence the dissolution of uranium that might hide the effect of whatever conditions you're adjusting. So I kept the iron constant. These experiments wasn't looking at that variable at the time. Temperature was set. Leached over a range of temperatures from 25 up to 95 degrees. 3 acid concentrations, 25 to 100 grams per litre sulfuric acid. These conditions were sort of roughly based on another paper published last year. It was looking at an actual ore specimen from Russia. So leaching took place in this small reactor. It's just a 1 litre temperature controlled lab scale leaching reactor built locally. And that was a sample, just a crystal of uranium brannerite. Brannerite itself is quite a dark green colour, but dark brown to black colour, but it's coated in a white alteration layer, which is apparent from this photo taken not long after the crystal was cracked open. Dark green brannerite coated in a very thin, light-coloured alteration layer. The brannerite was not too highly substituted. It's fairly pure. It's mostly uranium and titanium, some thorium, lead, calcium, some other minor impurities as well. But and the EDX spectrum agrees. It's mostly uranium and titanium with some thorium, lead, calcium. The main focus of the study was, of course, the kinetics. So these were some of the uranium extraction curves. For the high temperature curves at the top, sort of 52 degree leach curves in the middle, and the 25 degree leach curves at the bottom. I've left off the 36, 63, and 79 degree ones to avoid cluttering the slide, but they all fit the same sort of trend, with darker lines corresponding to higher acid concentrations. Just from this, it should be apparent that increasing the temperature had quite a large effect on the rate at which uranium dissolved. Increasing the concentration of acid had a slight but consistent effect on the rate of uranium dissolution. And there were similar trends observed with titanium extraction as well. Temperature had quite a large effect on the rate at which it dissolved. And the acidity also affected the rate of titanium dissolution, but a stronger effect in the amount that actually stayed in solution. Now, this effect is most apparent in the high temperature weak acid leach curve up there, in that titanium was frequently observed precipitating out after dissolving. So that was the secondary titanium dioxide product I was talking about earlier. So, yeah, the solubility of titanium will decrease with increasing temperature, and of course it's more soluble in concentrated acid. So unsurprisingly, it was in hot dilute acid that the greatest amount of titanium precipitation was observed, as it's most soluble in cold concentrated acid. So yeah, it's quite clearly precipitating out, and this was confirmed with the X-ray diffraction results and the electron microscopy as well. Similar sort of behaviour has been observed by other researchers working with perovskite and ilmenite. The mineral dissolves completely and then the titanium precipitates back out, forming a secondary phase. So yeah, in every single one of these leaching experiments, the titanium extraction was lower than the uranium extraction. Just selected EDX spectra of some of the residues. They're all normalised to that titanium peak there. Got the initial material at the back, the 52 degree residues in the middle, 96 degree residues towards the front. Now, the uranium peaks are much lower in the 52 degree leach residues and near absent from the 96 degree residues, which is a bit easier to see when we just look at the relevant area. The uranium peaks are much lower, sort of after leaching at moderate temperature, and are near completely absent from the high temperature residues. So at high temperatures, it's pretty much just complete conversion into titanium dioxide, with most of the uranium entering solution. Alright, so the initial rates of uranium and titanium extraction were fairly similar, though uranium was always slightly faster. The dissolution seems strongly dependent on temperature, and temperature had about the same effect on both uranium and titanium extraction rates, with about the same sort of activation energy for both. Activation energy being the energy taken to start chemical reaction. The higher the activation energy is, the more the rate will increase when the temperature is raised. Varying the acid concentration had a similar effect on both as well. When I looked into the actual effect of the acidity on the reaction rate, it came out similar coefficients for both metals. Under the harshest set of conditions I used, about 90% of the uranium was extracted within the first half hour. Uranium extraction was higher than titanium extraction in every one of these experiments, but the higher the acid concentration was, the more the titanium extraction approached that of the uranium extraction in the end. Titanium extraction was a lot more dependent on the acid concentration. Titanium dioxide is fairly insoluble, it's fairly stable in solution as well, and was observed to precipitate. This was confirmed in a few different ways. I've not shown the X-ray diffraction patterns up here, but quite a few of the higher temperature residues, there's a few fairly prominent anatase peaks, anatase being a form of titanium dioxide, the variant that forms when titanium precipitates from sulfate solutions. In chloride solutions, it tends to form rutile, different crystal structure. Electron microscope images, which I'll be going through shortly, show the formation of a secondary phase, and the spot EDX analyses show that the secondary titanium is forming as a separate phase. It's not forming on the surface of the brannerite, which is something we thought might happen initially. So the initial sort of unleached material is fairly jagged and angular under the electron microscope, the flat faces, sharp corners. In the next few images, I'll show the residue after 5 hours and 100 grams per litre sulfuric acid at progressively increasing temperature. And as these images, comparing these images, you can see the brannerite gradually becoming more and more corroded until it vanishes, replaced by something else in the end. So under fairly mild conditions, some of the faces of the mineral grains appear to have been attacked, whereas others are left intact. Not entirely sure why that's happening at this stage, but Also seems the lixiviant also seems to have been eating away at cracks within the mineral grains. Whether those cracks were always there or whether they formed during leaching, still no way of knowing just yet. And there's something similar at the next temperature up. Some faces attacked, some others left intact. By about 52 degrees, the residues had started appearing quite porous, but with a few particles that looked otherwise intact. So the surface is quite a bit more severely attacked in these conditions, 100 grams per litre sulfuric acid, 52 degrees, but there are a few particles that appear intact, and the contrast is a bit more obvious in this one. At 63 degrees, we've got a bunch of very corroded looking particles around the edge, with a few, like the ones in the middle, that seem relatively intact, which either survived the leaching process or formed during it. And based on the results I've been describing so far, I'm leaning towards the latter explanation, that they formed during the leaching. So when we did spot analyses on these ones, those corroded particles around the outside are near the same sort of elemental ratios as the initial unleached material, which says a few interesting things about the nature of the reaction mechanism. Particles like the ones in the middle are mostly titanium oxides with a few other insoluble things mixed in. I mentioned lead earlier, just sort of there as a radioactive decay product. Lead sulfate is insoluble, so it will not dissolve in sulfuric acid, so that tended to collect in some of these secondary particles as well. So yeah, the sort of reaction mechanism this points towards is one in which the brannerite becomes porous over the course of the leaching reaction, with the titanium and the rest precipitating out elsewhere in solution. And this kind of gradually becoming porous sort of mechanism where it sort of becomes corroded and pitted, gradually becoming porous, has been documented elsewhere as well in some qualitative leaching studies done in the past. After leaching at 79 degrees, there's none of the corroded looking brannerite there. At lower temperatures, the uranium extraction is about 97% at this point, very little of it remaining in the solid phase. So this is just mostly titanium dioxide and a few other things that didn't dissolve. And something similar at 96 degrees. This is mostly titanium dioxide with a few other insoluble materials in there, a small amount of silica, and the lead sulfate I mentioned earlier. Yeah, any lead in there would have very quickly solidified lead sulfate. So going back through the main sort of points, rapid and complete uranium dissolution is achievable with this sort of mineral phase. The rate of dissolution is very much dependent upon temperature. Titanium will dissolve along with uranium, that doesn't necessarily stay in solution for that long, forming a secondary titanium oxide phase. The concentration of acid is quite a strong effect on the amount of titanium that will dissolve and stay dissolved. And when it does precipitate out, it does so as a separate phase, not on the surface of the brannerite as we'd initially been concerned. Increasing the concentration of acid prevents the reprecipitation of titanium and has a slight positive effect on uranium extraction. A high free acid concentration seems to be needed in order to break apart the titanium lattice and get the uranium out into solution. So, yeah. Any questions?
Yeah, thanks. I enjoyed your talk. Sometimes in the real world, you find that there are interactions between the variables like pulp density, acid strength, time, temperature, etc. And the way around that is to use factorial, multi-factorial experiments to do that. Have you done any of that work?
No. Again, I was sort of had expected some degree of interaction between temperature and acidity, which is why I did it the way I did it. Didn't end up seeing any. So.
Thank you. I enjoyed the talk. You throw some light on the gangue mineralogy. Could you please tell us something about the gangue minerals?
Again, this was a pure crystalline specimen done specifically to avoid those kind of influences. That's what we're getting into later. At the moment, I just need to work out how it behaves on its own. So there's plenty of literature out there on this stuff.
If there's no further questions, I think you'll agree with me. Both talks were really excellent, dealing with, I suppose, very topical subjects, nickel laterites and refractory uranium. So would you please put your hands together to thank both Rorie and Anna for excellent presentations.